Welcome. In this book, Rocket Boys, Homer Hickam tells the story of his life growing up in a coal mining town. In 1957, the Soviets launched the Sputnik satellite, and this inspired Homer and his friends to form the Rocket Boys Amateur Rocket Club. After a little over a year of working, they realized they didn't have all the technical skills they needed to continue to advance in their rocketry. They had an influential teacher named Miss Riley who got together with the librarian to buy them a book called Principles of Guided Missile Design. And Homer wrote, "I flipped through the pages of the book, seeing chapter titles, amazing chapter titles, passing before my eyes. Then I read the most wonderful title of a chapter in any book I had ever held, Fundamentals of Rocket Engines. I felt as if she had just given me something straight from God. I don't know how to thank you," I blurted out. "All I've done is give you a book," she said. "You have to have the courage to learn what's inside it." Physics class is a wonderful opportunity to learn analytical skills as well as technical skills that will serve you well whether or not you choose a technical major. But you have to have the courage to learn what's inside it. I'm Dr. Courtney. In this problem, we are asked to interpret the motion of a model rocket that has been launched from the ground. As we interpret this problem, we realize that we're going to need equations of motion, which are also called kinematic equations. And we are specifically asked to find the maximum height of this rocket. Let's call that y max. And we're also asked to find the speed, which is the absolute value of velocity, and the position, y, at specific times, namely 1 second, 5 seconds, and 9 seconds. As we develop this problem, let's remind ourselves of a couple of things. First of all, velocity is a vector quantity that includes both magnitude and direction. Speed is only the magnitude portion of that velocity vector, so we express it as the absolute value of velocity here. Let's draw a picture of what's happening, and then we will make a point-by-point plan for how to evaluate it. The rocket is launched from the ground. It will rise and then reach some maximum height and fall back to Earth. Once the rocket is launched, the only forces acting on it are acceleration due to gravity that we are considering. So this type of problem is also known as a projectile motion problem. Let's draw a graph to help us understand a little bit better what is happening with the motion of the rocket. If we have time on the x-axis and the vertical position in meters on the y-axis, when the rocket is launched, it starts from the ground at time 0. As time progresses, it will rise to reach a maximum height and fall back to the ground. Now, I'd also like you to recall that velocity as a function of time is the first derivative of position as a function of time. Now, the first derivative is the slope of a curve, right? So if we look at this position versus time curve, the velocity is the slope of that curve. When the velocity is 0, here, that is the maximum height. This is going to help us as we formulate a plan for how to determine the maximum height. As we begin to evaluate a problem, what we first want to do is to look at the units, and make sure that the units of the values we've been given are in MKS units, and if not, to convert them. Next, we are going to need to express the vertical position y in terms of the initial velocity we were given, acceleration, and time. We will also need an expression for the velocity in terms of the initial velocity, acceleration, and time. As we've discussed with regard to the graph, to find the maximum height, we need to find the time at which the velocity is 0. So we will set the function that we find in part 3 equal to 0 and solve for time. Then we will substitute into our expression for y of t, the vertical position as a function of time that we expressed in part 2, to compute the maximum height. Moving on to the next part of the problem is a computational issue. So we will compute speed and position at t equals 1 second, 5 seconds, and 9 seconds by substituting into our expressions for velocity as a function of time and y as a function of time. Now that might take up a lot of space and it would be compact to express that as a table, so I'm going to make a note here that I would like to write that as a table to be efficient about it. That's not necessary to the physics, it's just a matter of approach. Once we have values, we need to determine how to express them in terms of significant figures. Intermediate calculations should retain significant figures, but then we want to check before we report our final numbers how many significant figures to use. Okay, as we evaluate this problem, we are going to start by looking at the units. The only value that we've been given in the problem is V0. Let's make a note of that here. And that was 73.5 meters per second, V0. And we can also make a note then that acceleration due to gravity is minus 9.8 meters per second squared. Why minus? Because we are assuming that vertical is the positive direction for position, and so since acceleration is acting in the opposite direction, we give that a negative value. So our units are check out that they are in MKS units already. Next, we need to express the position in terms of the initial velocity, acceleration, and time. The equation of motion that does that is we start at the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Our initial height is 0. We're counting the ground as 0. So then y of t becomes our initial velocity, 73.5 meters per second times time plus 1/2 the acceleration of minus 9.8 meters per second squared times time squared. We can further simplify that a little bit to 73.5 meters per second times time minus 4.9 meters per second squared times time squared. Then we need an expression for velocity as a function of time. Velocity is the initial velocity plus the acceleration times time, which in our case is 73.5 meters per second minus 9.8 meters per second squared times time. So now we have expressions for both position and velocity as a function of time, including the values that we've been given. What can we do with that? Well, now we're ready to set that velocity expression equal to 0 to find out the time at which the rocket reaches maximum height. So 0 equals 73.5 meters per second minus 9.8 meters per second squared times time. If we move 9.8 meters per second squared times time over to the other side, and then divide through by 9.8 meters per second squared, we find that the time to reach maximum height is 7.5 seconds. So this is part of our answer, but it's not the answer that we were asked for explicitly. We were asked to find the maximum height. And so to compute the maximum height, we need to substitute this value. So y at 7.5 seconds is 73.5 meters per second times 7 seconds minus 4.9 meters per second squared times 7 seconds squared. And that gives us a maximum height of 274.4 meters. So as we look at our significant figures, we were given an initial velocity of 73.5 meters per second, so we will report our answer to three significant figures as well. 274 meters. Now we can substitute values of time equal 1 second, 5 seconds, and 9 seconds into our expressions to find the speed, which is the maximum value of velocity in meters per second, and the height y in terms of meters. And time in seconds is 1, 5, and 9. And we compute those values to be 63.7 and a height of 68.6 meters at 1 second, 24.5 meters per second, and 245 meters at time is 5 seconds. And at 9 seconds, we have a speed of 14.7 meters per second and a height of 264.6, which rounds to 265 to three significant digits. So these are our answers. How can we determine whether or not they are reasonable? The final step of our problem is to assess our answer. First of all, we want to check our units. As we developed the expressions for position and velocity, we included units in the values that we were given. So when we have meters per second times seconds, that's going to give us units of meters here. Similarly, meters per second squared times time squared will give us meters. So our position equation results in unit of meters, which is what we would expect. Similarly, for velocity, when we have meters per second and then meters per second squared times seconds, we get final units of meters per second, which is also what we would expect. Now what about the magnitude or the progression of values in position and time? Let's go back to our position versus time graph that we made as we were developing the problem. We remind ourselves that the rocket is increasing in height but decreasing in speed prior to reaching its maximum height. After that, it will be decreasing in height yet increasing in speed again after 0. So if we make a note on our chart here, where is the maximum height with respect to these values? Well, the time was at 7.5 seconds, which is between 5 and 9, and the maximum height was 274. So we make a note that the maximum was in between here. So we expect that the velocity is going to be decreasing as we approach the maximum height, which it is, and that after reaching the maximum height it will be increasing again, which it does. Similarly, the height should be increasing as we approach the maximum height. That maximum height was 274. Then it should be below the maximum height again as we go beyond the time at which the maximum height was reached. So by unit analysis and by considering our answers with respect to the maximum height and the time at which that occurs, we develop confidence that our answer is correct.